All right, well, I think we'll start. We're going to be talking about even more colorful things today than yesterday, non-perturbative aspects of PP collisions. So last time, and with the previous lectures in QCD that you had, you've understood about Parton showers and the basics of hadronization, confinement, string fragmentation, or cluster fragmentation at least. So we've got all of these components ready, and we sort of understand them, and we can try to put a hard scattering in a PP collision, just using PDFs, calculating cross sections, showering it, and string fragmenting it, and see whether that can describe data. And what happens is what we see here. So these different models are, if you have just strings, you have these two models here without showers, strings with showers, so hard interactions with showers is this dashed line here that gives you a bit more. But the data has extremely large fluctuations. This is a plot of just the charged track multiplicity distribution. It's usually the first thing that any given collider measures when it just switches on. The tracker is working, you count the number of tracks, and you plot the distribution of the number of tracks. And you can see that it's a very, very wide distribution. Some events have almost no tracks in them, and some events have very, very many. And if we just stick sort of QCD 2-to-2 scattering processes with showers and string fragmentation, we see that we can sort of get the average right. Maybe this line has about the right average number of tracks, but it does not describe the incredibly fluctuating nature of the actual distribution that we see in the data. Another thing we see is over here on the right. It's called the forward-backward correlation. So you take two bins in the detector, and you take them apart by a certain number of units in pseudo-rapidity. So you correlate a bin at minus eta over 2 with a bin at plus eta over 2, and you see how correlated are they. And you can see that the data exhibits quite large correlations over many units in rapidity. Whereas the models, if you add showers, perturbative stuff, mini jets, you can see that you get some local correlations when the bins are close. There is a bit of correlation here, but it quickly dies away, just as you would expect for perturbative, localized, jet-like, some localized lump of energy density. It quickly dies away with rapidity. And if you don't have showers even, then of course you don't get much correlation at all. You just have the strings producing this flat rapidity plateau with almost independent fluctuations. When you're far away from this region of the string, doesn't know what that region of the string is doing. But in the data, there's something that tells the whole event to fluctuate up and down, which you see in this very large correlation. So, okay, so we can get about the right average, but there's much bigger fluctuations. Something else is fluctuating than anything we've learned about so far. And something is telling the entire event to fluctuate up or down over many units in rapidity. So that was already known a long time ago, right? This is 1981, 1982, just when Monte Carlo event generators were starting to be created. And so this was a very early question that people were asking, what apparently we can't describe hadron collider data with everything that we have discussed so far, showers, hadronization, and everything else. I would say this is exciting, right? When you see models, physical models, even though you've spent a lot of work on them, fail this spectacularly, this is not a subtle effect. This is really big. And that's actually really exciting, right? That's what we want when we're looking for BSM physics and stuff. We want to see the standard model fail. We want to see our models fail because that's how we learn new things. So this is really exciting, seeing models that are based on sound physical principles that we thought we had understood completely fail to describe data. So usually that points to more interesting physics. So there's further evidence here that I'll mention of additional physics going on in hadron-hadron collision. That's called the Pedestal Effect. Today we call it the underlying event. And that was also right around the same time discovered. So UA1 were doing PP bar collisions at 540 GeV center of mass energy. And they could study jets with energies up to 100 GeV, so quite hard jets by the standards of the day. And they got plots like the one on the right here. And what you see is that these little circles that they've plotted is if they just take random collisions, so they just what's called minimum bias. So no trigger bias, they're not triggering on any hard objects, they're just sort of looking at the average collision. This is the average energy density or track density. This is average number of charged tracks as a function of pseudo rapidity that they see when they just sort of take random collisions, minimum bias. That's the sort of overall energy level. But when they then trigger on hard jets, you see this solid histogram here. And you see that far from, so there's obviously a jet here. That's what they triggered on. But far from the jet core, there is a sort of ambient level, which is higher than what they see in minimum bias, substantially higher, maybe a factor 2 or something like that. And then there are some, whatever, Monte Carlo that can fit that, but that's not something that we would use today. So I'm not going to go into that. But you can see that it looks like this jet is sitting on a pedestal of higher than average activity. And so this was from the abstract of the paper. Outside of that, a constant ET plateau is observed, whose height is independent of the jet ET. So if they triggered on very hard jets or softer jets, this plateau, the jet would go up and down, but the plateau would stay about the same. And it would always be higher than minimum bias. Its value is substantially higher than the observed in minimum bias. So hadron-hadron collisions, hard jets sit on pedestals of increased particle production that extend far from the jet cores. And as I said today, that's what we call the underlying event. So what is minimum bias? I've used this word a little bit. Don't know if you all know what it means. It's a simple question. What does the average LHC collision look like? The word simply originates with imposing the minimal trigger bias that you can. So there's also something called zero bias, where you simply trigger on the clock. So you know when your bunches are crossing. Some of those bunch crossings will be empty, so you'll have some zero bins in a zero bias sample. Minimum bias is you have some forward counters. I forget what they're called in the various experiments, but some scintillator plates or something in a very forward direction. And basically, if anything interesting happened or any sort of scattering or exchange happened in the center of the event, then something will hit those plates, is the idea. Most events, so you'll capture most of the inelastic cross-section. So it's not quite zero bias, there is a little bit of bias. Therefore, this definition is also a bit experiment dependent. It's exactly how big are your plates and where are they sitting and what's their acceptance and so forth. But it's the minimal trigger bias that you are able to impose in a given experiment, very close to zero bias. So think about minimum bias as just requiring that at least some charged particles had been scattered into the event. So, okay, so let's look at this pedestal that we've seen in the UA1 data. So again, here we have our rapidity coordinate that we discussed last time. We have a jet that's sticking out of it with lots of particles there. And then we have this plateau, which we call the pedestal or the underlying event. So that looks a lot like this constant rapidity plateau that we discussed when we discussed string fragmentation. But the funny thing is that this underlying activity, this plateau, is much higher than for a single string. So if we want to stick with something that is sort of string-based or build this underlying event up with strings, could there be multiple strings here, several strings? That's at least a naive idea that we could have if we wanted to build up this kind of underlying activity underneath the jet. So then we go to a motivation for why one would consider multiple strings in the context of what's called multiple Parton interactions. So we look at the total inelastic PP cross-section. So proton-proton cross-section, the total inelastic cross-section at 8 TeV is about 80 millibars. And that can be measured, so we don't have to calculate anything. There are also fits and so forth, and you can calculate it, but you can also just measure it. It's about 80 millibars. That's the total PP cross-section at LHC energies. And we can compare that to the total 2-to-2 scattering cross-section in QCD that we would calculate perturbatively. We know that at some PT that's going to break down, but let's just see as a function of the PT of the scattering, the t-hat Mandelstam variable, how big is this Parton-Parton cross-section, and we can try with different PDF sets. That's going to change a little bit what the cross-section will be. We can change what alpha S is and so forth, so we'll get some variation. So here I've just plotted two different perturbative calculations for the 2-to-2 cross-section calculated in perturbation theory, integrated above some PT min. And you can see that at PT min equals 20 GeV, that's about 1 millibarn. So it's a small fraction of the total inelastic cross-section that have scatterings that are, above PT of 20 GeV. But as we go down, we see that at some point we actually saturate the total cross-section. So at PT of 4 GeV, this perturbative leading order prediction is of the same order as the total inelastic cross section. And then it becomes even larger. Now, the interesting thing here is that at some point, of course, we will expect the perturbation theory should break down, because gluon wavelengths that are bigger than the proton should not be able to resolve color charges in the proton. But this is happening at a scale of 4 GeV. It's not quite lambda QCD, right? It's 10 times larger. This is actually a perturbatively large scale. We would expect perturbation theory to be working more or less at 4 GeV and break down later. So this is an interestingly large scale that this breaks down. So how can we make sense of the fact that the Parton-Parton cross-section is exceeding the hadron-hadron cross-section at some perturbatively large scale? One way we can make sense of this is by thinking about what does a cross-section actually measure? What does a cross-section mean? We're comparing a proton-proton cross-section and a Parton-Parton cross-section. And once we multiply cross-sections by luminosities, we get numbers of scatterings, right, essentially. A proton is a beam of partons. What if in each proton-proton collision, I have several Parton-Parton scatterings? Then the Parton-Parton scattering, I would have more Parton-Parton scatterings than proton-proton scatterings. And that is one way of making sense of this, that what it's telling us is actually not that perturbation theory is breaking down, but that each proton-proton collision is going to have several Parton-Parton scatterings with PTs of order this scale in it. So that's the sort of fundamental motivation to multiple Parton interactions inside of a single proton-proton collision to make sense of this Parton-Parton versus proton-proton cross-section. It also just physically, naively has to happen because protons are composite. When we smack them together, why should it always be so that only a single Parton-Parton pair in there collides? So multiple Parton interactions has to happen at some level. It's just a question of how often, and are they important for phenomenology or not when we calculate these things. And this observation here would argue that probably they are important phenomenology. And then we start thinking, okay, if we can have multiple Parton-Parton, multiple color exchanges, maybe that's what's building up this underlying activity that's larger than what we have in minimum bias. So that's what we think is the physics of the pedestal today.